Here I have a Matchless Hotbox bought from the US back here to Australia. I've taken it apart and I'm going to put it back together, starting with the power supply. I have a schematic here showing the power transformer, the primary winding and two secondary windings. To wire it for 100 volt mains, we'd hook up the black common wire and the purple wire. And to wire it for 120 volt mains, we'd hook up the black common wire and the brown wire. Putting AC in will induce AC out. We should get over 300 volts on the winding that supplies the B plus to the plates, and we should get 6.3 volts on the winding that supplies power for the lamps and the heater filaments. Put AC in, we get AC out. If we ground this center tap, with these two diodes we'll form a full wave rectifier, which turns the AC into DC. So we'll have AC here and then DC from here. I've replaced this first filter cap and I've added a 270k bleeder resistor to drain the cap when the power is switched off. This is the power transformer here. You can see the primary taps, the black, the purple, the brown. There's also an orange wire here. I'm going to try to figure out what that is using a 12 volt transformer similar to this one. Bought at JCar for about $17. The three red wires you can see here are the secondary taps that supply the high voltage B plus to the plates. I've got one wire connected here, then across a diode to the first node, another connected here across a diode to the first node, and the center tap comes around over to the ground connection over here. The first filter cap's wired in. The positive lead goes to the first node and the negative lead goes to this ground lug here. I've also got a 270k bleeder resistor here going from the first node down to the ground. That's to drain the capacitor when the power's switched off. These three green wires here supply the 6.3 volts to the heater filaments and to the lamps. They're coming over here to a bridge rectifier. AC's coming in on this lug and AC's coming in on this lug, and DC will come out this two lugs here. The capacitor goes across the two DC terminals and the center tap's ignored. Here's the center tap here. It's not wired in because this bridge rectifier is essentially 4 diodes and creates a full wave rectifier. Okay, let's try this power transformer out with 12 volts AC. Got a multimeter, I turn it on to AC volts. Connect the black lead to this yellow wire, other lead to the other yellow wire, and you can see it's putting out a bit over 12 volts, 12.5 volts AC. Take the black lead and put it on the ground lug. Take the red lead, put it onto the first node, set our multimeter for DC, okay, I'll put this 12 volts where we should be putting 100 volts, 100 volt mains taps, so I'm putting in about 1/8 of what we should be putting in, and I'm getting about 41.5 volts. So if we put 100 volts in there, we'd probably end up with 8 times that, about 330 volts. We'll try it on the 120 volt mains. Okay, we're putting in about 1/10 of what we should be putting in. We're ending up with about 34 volts. So if we put in 10 times that, again we'll end up with about 340 volts. So we're probably looking at trying to get 340 volts on this orange wire. Okay, the cap's drained down and you can see we've got 17 volts by hooking up the orange wire, so we'd have to put in about 20 times 12 volts to get what we were getting on the other two terminals. So I'll try that out with 240 volt mains. Here's a drawing of a bridge rectifier. The 4 diodes, the 2 AC terminals where the 6.3 volt secondary windings are connected. That's them there. The negative and the positive terminals. Here's a drawing of the lamps and tube heater filaments. This is one of the terminals of the lamp. Here's another terminal with the filament going across it. This is pin 4, pin 5 and pin 9 of the tube socket, with a filament going between pin 4 and pin 9, and another filament going between pin 5 and pin 9. Pin 4s and pin 5s are all tied together, and the pin 9s are tied together and connected up to the lamps. So this is wired in parallel. The lamp will draw about 250 milliamps each, and the heater filaments will draw about 150 milliamps each. So that'll be a total current draw of a bit over 1 amp. Each end of this is connected to the positive and the negative terminal of the bridge rectifier. The hot box is plugged into the 240 volt mains. There's a multimeter connected to the DC terminals of the bridge rectifier. The orange and the black primary taps are wired in, the unused taps are capped off, and there's a fuse in series with the primary windings. I'll turn the power on. You can see about 8.7 volts on the filament supply. The voltage is high because the circuit's unloaded. There's nothing drawing any current. So let's hook up the filaments and draw some current. You can see we've brought that down, brought the voltage down. We can test the current draw by putting a multimeter in series with the circuit. So we disconnect it. Connect up these two. And we can see it drawing a little over 1 amp. 6.3 volts there and 312 volts there. I'll switch it off. The hot box uses 2 twin triad tubes. Twin triad means there's 2 tubes in each glass envelope. 2 heaters, 2 plates, 2 cathodes. Commonly drawn on schematics as 2 separate triodes. They may be placed near each other in a circuit or separated by a tone stack or a reverb tank or the like. The cathodes, pin 3 and 8, go through a cathode resistor to ground. They're sometimes bypassed by connecting a capacitor in parallel. The capacitor blocks negative feedback, which increases the gain. Larger value capacitors will allow more bass through. To test these capacitors, you need to remove them from the circuit or at least lift one of the legs. All these capacitors were tested and found to be good. I did replace the 1UF electrolytic here with a Nikon Muse. The electronics don't last forever, and the one in there was 15 to 20 years old. The plates, pin 1 and 6, are connected to the voltage rail, usually through a plate load resistor. From the voltage rail here, connects to B, directly to pin 6, and through the 100k resistor to pin 1. This blue wire here connects to pin 6 through this 100k resistor to pin 1. I'll test the resistors now. The 4 cathodes all connect here. I've got them connected to the common terminal of a multimeter set on ohms. I also have the wires from the plates connected to the common terminal of the multimeter so I can test them all at once. Pin number 1 is the plate, so it should read 100k. 102, that's good. Pin 2 is the signal grid. Pin 3 is the cathode at 1.5k. Pin 3, 1.5k, that's good. Pin 4, that's the heater filament circuit. Should be open. We should have no connection there. Same with 5. And same with 9, there should be no connection. That's all good. Number 6, we should have a direct connection. So it should be nearly short circuit, or similar to if we connect it direct up to the multimeter, 0.1, 6.1, so that's good. Pin 7 is the signal grid, we'll leave that. And pin 8, the last cathode at 56k. Pin 8, 59k. That's good. Carbon comp resistors tend to drift north a bit, so they're always a little bit high. I'm going to connect this multimeter up to check the mains voltage that's coming into this preamp. This brown wire here is the active wire. It's connected to the red wire through a fuse to the orange wire on the primary side of the power transformer. The blue wire here is the neutral wire. It's connected to the black common wire on the primary side of the power transformer. And the green and yellow wire, that's the earth, and it's soldered to a lug that's bolted to the chassis. Okay, we'll get this black common from the multimeter and connect it to the neutral. We'll get the red wire from the multimeter and connect it to the active. Okay, I'm going to connect this multimeter between ground and the first node. This is just for safety, so we know if there's any charge in the caps at all times. Okay, this multimeter here, I'll use this to probe for different voltages. It goes to the ground. The cathodes will need to be grounded. I'll run a wire from the cathodes to the ground lug. I've got the plates connected through two 10k resistors to the yellow wire, which I will connect up to the first node. The orange wire runs through an ammeter and then out to the 10k resistor, and the blue wire is connected up directly to the 10k resistor. The heaters are all connected up. Time to switch it on. The hotbox is running like it was in standby. The heaters are connected and switched on, but the tube plates aren't connected. There's 240 volts at the mains. This will vary from 230 to 240 volts. As it varies, it'll affect the voltage at the first node. When I connect the tube plates, they'll draw a current, placing a load on the secondary windings. This will drop the voltage at the first node from 311 volts to 292 volts. We've dropped nearly 20 volts. I'm going to find the current draw of these two JJ 12AX7 tubes by measuring the voltage drop across each of these 10k resistors. I'll try the first node side. It'll be the same voltage as the first node, 294 volts. I'll try the other side, 262. We're dropping about 32 volts across this 10,000 ohm resistor. Ohm's law tells us that current equals voltage divided by resistance. So 32 volts divided by 10,000 ohms equals 0.0032 amps or 3.2 milliamps. Now I'll measure the voltage drop across the other 10,000 ohm resistor. You can see we're dropping about 8 volts across this resistor. 8 volts divided by 10,000 ohms is 0.8 milliamps. So the tube's drawing around 0.8 milliamps. Similar tubes may not draw similar current. So I'll retest for current draw using these two RCA 12AT7 tubes. I'll also hook this multimeter directly across the 10,000 ohm resistor and measure the voltage drop directly. I've removed the JJ 12AX7 tubes and installed the RCA 12AT7 tubes. I've connected the multimeter directly across the 10,000 ohm resistor, and across this resistor I'm dropping 33.3 volts, which means I've got one tube drawing 3.3 milliamps and the other tube drawing 1.4 milliamps. If I was to measure the voltage here, here or here, I'd get a first node voltage of 289 to 293 volts. On the schematic we're looking for around 242 volts at node 2A and 250 volts at node 2B. With a 12AX7 in, we're drawing 0.8 milliamps across this resistor here. If we were to use a 22k resistor here, the voltage we'd drop across it would be 0.8 milliamps times 22k, which would equal 17.6 volts. Dropping 17.6 volts off the first node voltage would give us around just over 270 volts here, which is a little bit high. So I've put a 46k resistor in here. This will drop around 36 volts. 36 volts off our first node voltage will give us about 253 volts here at node 2A. If we were to use a 4.7k resistor here, we would drop around 15 volts. 4.7k times 3.2 milliamps is 15 volts, which still isn't close enough. So I'm going to leave the 10k resistor in here. 10k times 3.2 milliamps is 32 volts. 32 volts of 289 volts will be to about 257 volts here at node 2B. There's an Electro-Harmonix 12AX7 in the A tube socket. A 46k resistor going from the first node to node 2A. A 10k resistor going from the first node to node 2B. There's 289 volts at the first node, 253 volts at node 2A, and 256 volts at node 2B. Okay, these voltages are safe. They're a little bit high, but a 12AX7 can handle up to about 320 volts at the plate, so these voltages are good. I had 154 volts at the plate, Matchless specs 123 volts here, and biased a little bit warm I had 0.86 volts at the cathode. I tried 6 different tubes in the Hotbox, 3 brand new 12AX7s and 3 older preamp tubes. With the lowest current draw indicated by the smallest voltage drop from a tungsol 12AX7, then dropping 33 volts was a JJ 12AX7, dropping 36 volts, the Electro Harmonics 12AX7, dropping 37 volts, a Tesla 12AX7, dropping 41 volts, a GE 5-star 5751, and dropping 52 volts, the RCA 12AT7. Just by swapping tubes out, the voltage at node 2A went from 257 volts down to 237 volts, and the voltage at the plates went from 168 volts down to 106 volts.